Imagine you are a marine biologist diving off the coast of Indonesia. You collect a sample of soft coral, nothing special, just a rubbery organism swaying in the current. You bring it back to the lab, run extraction, and the outcomes are molecular unlike anything you have seen before. No oxygen, no nitrogen, no sulfur, no functional groups of any kind, just carbon and hydrogen. 15 carbons arranged in a ring with 4 double bonds scattered around it. Scientists named it Flexibilene after coral genus Eunicea flexibilis. Now, here is the question that should keep any synthetic chemist up at night. How do you make this in the lab? In classic retrosynthetic analysis, the approach developed by E.J. Corey that won him the Nobel Prize. You work backwards from your target. You look for functional groups. You identify bonds to discollect. You find your starting materials. But flexibility has no functional groups. There is nothing to discollect in the classical sense. The molecule is just a hydrocarbon ring with double bonds. On top of that, it has 15-member ring. And the macrocyclization reactions are notoriously difficult. When two ends of a known chain need to find each other and bond together, entropy works against you. The chain is floppy, the ends are far apart, and the reaction is slow. And those 4 double bonds, each one is tri-substituted with E geometry. Getting one of them wrong and you do not have flexibility. You have a different molecule. As we just saw, building this from scratch is a structural nightmare. But today we are going to walk through John McMurry's 1983 masterpiece. We are going to build this entire molecule from the ground up using exactly 7 distinct transition metals. Let's see exactly how he pulled it off, starting with metal number 1, lithium. To build our first fragment, we need to attach an epoxide to this alkyne. But here is the trap. The terminal proton is 10 billion times more acidic than the rest of the molecule. If you just one equivalent of butyllithium, it rips off the terminal proton. The epoxide attaches to the end of the chain, creating a useless internal alkyne that completely ruins the rest of our synthesis. So, what is the master move? We drop in exactly 2 equivalent of butyllithium. We sacrifice the first equivalent to protect the terminal alkyne, forcing the second equivalent to form a highly reactive dye, anion. The second negative charge slaps open the epoxide, leaving our precious triple bond completely untouched for a clean 78% yield. Number 2, chromium. Now that we have our primary alcohol, we need to oxidize it up to an aldehyde. We bring in pyridinium chromium chlorochromate or PCC to do the heavy lifting, but an aldehyde is way too reactive to survive the organometallic cross-couplings we have coming up next. So we immediately knock it in a void by turning it into a dimethyl acetal. Now, here is the craziest part of this total synthesis. In this entire 15 carbon 7 metal masterpiece, this acetal is the only protecting group used, a clean 57% yield. And fragment 1 is officially locked, loaded, and ready for the heavy artillery. Metal number 3, zirconium. We have our protected alkyne, and now it is time to set up geometry for our final macrocycle. We bring in Schwartz reagent. This massive bridged zirconium diamond. Why use this bulky metal complex instead of standard hydrogenation? 2 reasons: radiochemistry and stereochemistry. The bulky zirconium atom specifically hunting down the least hindered spot, the very end of our terminal alkyne, as it adds across the triple bond. The massive cyclopentadienol rings physically force the carbon chain into a strict trans or alkene geometry. Look at the molecular 4. We now have an activated geometrically locked organozirconium species. Fragment 1 is perfectly primed, and it's time to pass the baton to Palladium for the cross-coupling. Now zoom in to the exact moment these two fragments collide. We aren't just mixing chemicals, we are orchestrating a precise organometallic handoff. We have our active pi-anyl palladium complex. The palladium has locked onto the allylic system, stripping away electron density and turning that carbon into a massive electrophilic target. Welcome to the climax of step 4. We have two heavyweight perfectly staged. Up top in green, our highly reactive pi-anyl palladium complex. Down below, our geometrically locked organozirconium missile. Through transmetallation, the zirconium hands its 7 carbon chain over to the palladium. But to get these two massive chains to finally slap together, the palladium needs a trigger, maleic anhydride. Because maleic anhydride is incredibly electron poor, it acts like a molecular sponge. It pulls electron density away from the palladium catalyst, forcing the metal to execute a rapid reductive elimination. The palladium instantly files the 2 carbon chains together and drops out of the cycle. The result? A flawless 76% yield of molecular 6. And as a beautiful bonus from the reaction woke up, our acetyl protecting group falls off for free. The aldehyde is revealed, and we now have a 15 carbon chain perfectly primed for the final ring closure. Welcome to the grand final. Metals 5, 6, and 7, titanium, zinc, and copper. We have our 15 carbon chain perfectly assembled, and with an aldehyde on one end and a ketone on the other. But closing a massive 15-member ring is notoriously difficult. Entropy is fighting against you, and the chain just wants to flop around. How do you force it to bite its own tail? The McMurry Coupling. John McMurry literally used his own namesake reaction to finish his masterpiece. Look at the top equation. To make this work, we need a battery. We use a zinc copper couple to aggressively pump electrons into titanium trichloride, reducing it down to a supercharged, highly reactive titanium 0. Now for the main event. This supercharged titanium physically grabs our aldehyde and our ketone, temporarily locking them into a 5-membered methanol cycle you see highlighted in green. But here is the thermodynamic secret. Titanium loves oxygen more than almost anything in the universe. It physically rips both oxygen atoms completely out of the carbon skeleton to form rock-solid titanium dioxide. The ring violently collapses, zipping the 2 carbon ends together to form our final double bond. 7 distinct metals and absolute synthetic mastery. We have successfully synthesized Flexibilene. If you made it all the way to the end of this 15 carbon, 7 metal marathon, your chemistry stamina is top tier. I am building a community of the most dedicated chemistry minds on YouTube. If you want to master more legendary total synthesis and deep dive reaction mechanisms, hit the subscribe button right now. Let me know in the comments which impossible molecule we should build next. I'll see you in the next masterclass.